We are going to begin talking about acids and bases as well as acid-base equilibria. We learned about chemical equilibrium in the previous chapter, and you will see some common threads throughout this chapter as well in regard to shifts in equilibrium. In order to get there, we need to go back and review some key concepts on acids and bases, as well as learn some new ones. Today's lesson should be relatively straightforward, but it's really important that you keep up with this chapter because it's going to build quickly. And if you don't understand the first parts of it, the latter parts will be extremely confusing. First thing we want to talk about are some basic definitions of acids and bases. We're first going to get into the Arrhenius definition. And with the Arrhenius definition, what are we focusing on? So you're going to look at what gets generated. So in regard to acids and bases, with the Arrhenius definition, you're focusing on what gets generated. So for example, an Arrhenius acid is one that generates protons when the acid's in aqueous solution. So for example here, you're going to generate proton or hydronium ion. As such, you also can show it this way. And again, a proton or a hydronium ion gets generated, and it's an aqueous solution that is dissolved in water. A strong acid ionizes completely, so you only have the arrow in the forward direction. And keep in mind with a strong acid that the concentration of the acid is equal to the concentration of proton. So this would be a strong acid. With a weak acid, the acid does not ionize completely. For example, if you had acetic acid, this is an equilibrium reaction that lies far to the left. You generate, you want me to do proton first? I'll do proton first. You generate, it doesn't really matter, proton and an acetate ion, and these concentrations are not equal. That's what you're going to start to see today and next time. You do need to know your strong acids. What are your strong acids? So you've got hydrochloric, hydrobromic, hydriodic. Those are your halide containing, if you will. You've got sulfuric. That's the only diprotic. Strong. You've got what? Not phosphoric. Phosphoric is weak. Nitric. Chloric. And periodic.
Teachers, please pardon the interruption. Teachers, please release your EMR students from their 7th period class in order for them to attend the EMR training in the cafeteria at this time. Thank you, and have a great day here in Cobra Country.
In regard to bases, if they're Arrhenius bases, they generate hydroxide ion when dissolved in water. For example, if you had sodium hydroxide, you have sodium ion and hydroxide ion. This one is a strong base, meaning that it ionizes completely. And these two concentrations would be equal as well. And we'll talk about some of the other bases in a little while. The Bronsted-Lowry definition this focuses not on what's generated, but transfer of protons. So you'll recall that an acid is a proton donor, and a base is a proton acceptor. For example, hydrochloric acid reacting with water. This is the acid, this is the base. The acid donates the proton to the base. The base accepts the proton. When the acid donates the proton to the base, the acid forms what's known as a conjugate base. And the base forms a conjugate acid. There are many, many examples. For example, if you had ammonia and water, and let's say that ammonia is acting as a base, it would accept the proton from water. The ammonia would form an ammonium ion. That's the conjugate acid. This is the acid, the proton donor, and it forms the conjugate base.
Isn't ammonia one of the ones that go either way?
Ammonia and water can act as acids or bases. They're what we refer to as amphiprotic or amphoteric, and they have the ability to act as acids or bases. Ammonia generally is categorized as a base, but it does have the ability to act as an acid because it can donate or accept. If they ever ask you about conjugate acid-base pairs, they're talking about what goes together, and that was a question on an AP exam very recently that the kids made a complete mess out of because the concept wasn't made clear to them. Can't remember what year it was. I'll have to look at it. It's either 14 or 15. And these examples are also illustrated in your notes here. You can see the acid donates the proton to the base. The base forms a hydronium ion, a conjugate acid, and the acid forms the conjugate base, chloride ion. It forms a coordinate covalent bond, and that's because the oxygen that had two lone pairs on it basically shares both of its electrons with the hydrogen. The hydrogen didn't have one to share. And another example here, that's actually the one I drew out. So you want to be comfortable with these conjugate acid-base pairs. Here's acetic acid acting as an acid, donating its proton to the base. Keep in mind when you have these Cu groups, the donatable proton is off that Cu. Okay? Amphiprotic or amphiprotic or amphoteric, these are all examples of substances that can go either way. Let me pick, for example, hydrogen sulfate ion so you could see it.
The shine is changing.
Right, so you want to be careful with that. For example, if you had this substance This has the ability to be an acid. An acid's a proton donor, so it's going to kick out the proton, if you will, and form a sulfate ion. This is its conjugate base. Alternatively, hydrogen sulfate ion can accept a proton, so it can act as a base and form sulfuric acid, a conjugate acid.
Those both reacting with water, right?
They can react with anything. For example, I shouldn't say anything, they can react with a base, a substance that can accept a proton. For example, if you had this substance, if this were acting as an acid, it would donate the proton to here. And it's funny drawing the lines like that. I'm showing it's giving it up, but actually the lone pair attacks and pulls it off, if you will. So don't let these arrows confuse you down the road. You won't see electron pushing at this level, but it comes into play in organic chem. So that would be an example where the hydrogen sulfate ions acting as an acid, generating conjugate base. The base accepts the proton from here and forms the conjugate acid. Alternatively, you could have done it this way. If you want this to be the base and this to be the acid, the base can accept a proton forming a conjugate acid, sulfuric acid, and it accepted it from ammonia acting as an acid in this case. So what's going to happen here is it donated as such. Just remember, when you accept a proton, your charge goes up by 1, more positive if you will, or less negative. When you donate a proton, so you lose it, the charge is going to decrease or become more negative. So be careful in terms of increase, decrease. So there are a couple of examples shown here. Let's make sure we can do this. This again is all honors level work. Looking here, my approach is to compare the two substances that look similar because they're going to represent a conjugate pair. So I look at the ammonia and I look at the ammonium ion. Has it donated or accepted? Accepted. So ammonia's the base and ammonium ion's the conjugate acid. And you can see that this donated, so hydrogen carbonate ion or bicarbonate ion is the acid and this is its conjugate base. Here's phosphoric acid. This has to be an acid, and this came up one year. The kids are like, well, how do you know?
It's filled up.
Right, it's filled up with protons. So you know phosphate ion is 3-, and it's not very often that you can gain more hydrogen than the charge predicts. The only examples I can think of is that you can get hydronium ion, and you can get ammonium ion. Those I think will be the two exceptions, but that's how you know this has to act as an acid because it can accept more H's. We're also going to draw these out because this comes into play as well.
We have to predict, right?
Yeah. So here you've got, you can tell this is an acid anyway because it donates a proton to water. Water then is the base. Here's its conjugate acid. This is the acid, its conjugate base. So you want to be comfortable with those pairs. Very, very straightforward. The next piece of the puzzle is going to look like a KEQ expression. This is going to be very simple for you as well. I'm going to backtrack for 1 sec because I know there was a question I want to think it may have been 2004, 2014 rather. I know it's off the new exam, and I was surprised the kids across the nation struggled with it. That's not the right document.
So did the exam?
Say it again?
Did the exam get harder?
Oh yeah. When they changed the format, it's not just, you know, plug and chug and pop an answer out. It's, here's the question right here. My memory is surprisingly good. So this is a very, very easy question to start it off. Off the 2014 exam, this is the new exam. It says, identify a Bronsted-Lowry conjugate acid-base pair in the reaction. Clearly label which is the acid and which is the base. And maybe because of the writing, the kids were confused, but you've got to go after the pair, okay? And there's more than one answer here. So if you went after this, what is that? That's an acid. You've got a clue group on there. And what's its conjugate base? This piece, right? So the pair would be this and this. You would have labeled acid and conjugate base, and they didn't ask you to explain. Pretty easy. You could have gone after the water and the hydronium ion, with this being the base and the hydronium ion being the conjugate acid, okay? And then it's asking for a Ka value, and you're going to learn how to do that. It looks hard, but it's not. All right, so the first thing we want to learn how to write is an acid ionization constant, also known as an acid dissociation constant. So very straightforward here. This is a KEQ expression. It's specialized for an acid because you start with an acid. So what you have here is acetic acid reacting with water to form acetate ion and hydronium ion. Your KEQ expression, products over reactants. Why do I not have a reactant in there? Because it's liquid, and you don't include liquids or solids. And this is where I said what you learned in the previous chapter is going to come back. Say it again.
The concentration remains constant.
Right, so that you're not interested in liquids or solids, no change in concentration. And these acid ionization constants have values, and these values can be found in your textbook. Now on the exam, they're going to give it to you straight up. In the homework problems, you may have to grab a Ka or Kb from the, I have the page numbers in here as well as the appendices. We'll look at that in a minute. If you have a base, keep in mind you're generating hydronium ion as opposed to proton, or let me rephrase. You're generating hydroxide ion as opposed to hydronium ion or proton. I think my head got ahead of myself. Again, bases, base and conjugate acid, so your two products in the numerator over the base you started with here. Now, it is a coincidence that the Kb and Ka values are identical here. They're not usually. It's just the example that I use. And you can find these in the back of your book. We'll be getting them into them much more.
So the values you need for each substance? Like,
yes.
You're not going to change ever? It's like always the same?
As long as the temperature is constant.
It's like any fluid.
Exactly. This is looking a little more difficult. I'll do the first one with you, and then you'll walk through the second one. It says, write the acid or base ionization constant of propanoic acid. Let's take a look. When you go to do this, the first thing you want to do is write the equation, and this is the way your mini quiz is going to open up. You're going to have to write an equation, and for the most part the coefficients are 1, so the balancing is already done for you. But they mention propanoic acid, and before I write that acid or base ionization constant, I'm going to write the equation reacting this acid with water This is the ionizable proton. I do know that equilibrium lies to the left. It will unless you have a strong acid, which you do not here. Propanoate ion and hydronium ion. And again, an acid will generate proton or hydronium ion. The acid is the proton donor. The base is the proton acceptor, which forms the conjugate acid, hydronium ion. That's the equation. The acid or base ionization constant, this is an acid. Ka is equal to concentration of propanoate ion times hydronium ion over concentration of the acid. Piece of cake, right? You try the second one. It says write the acid or base ionization constant of methylamine. And that word, if you watched Breaking Bad, you would have heard before. So write the equation. Now you've got a base here, so make sure you do the right thing.
How do you know that's a base?
Amines or bases.
Amines?
Amines, methylamine. When you have NH, N, NH, NH2, NH3, typically acting as a base.
Anything with amine is a base.
We're going to hit amines in a sec, but amines are bases.
So can we pick any acid we want, technically? Oh, so we don't have to use water?
That's not what he was saying. He's saying, could you pick any acid or any base, but you react it with water if you're showing ionization.
That's what I'm asking.
Yeah, what I said, right?
No, if we could use water.
Oh, no, when you're doing ionization, use water. I'm sorry. That's what I got. Is that what you got?
Yeah.
Want to point out a few things because one of the kids was very disappointed when I marked her equation wrong. She's like, I only forgot a charge. Well, if you forget a charge, you're not balanced. So, no. All right? You're generating ions, aqueous. Okay. We're going to look briefly at how molecular structure affects acid and base strength. We're not going to harp on much of this because I don't think it's going to come into play that much except one aspect. All right, this could come into play. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. For example, if you had this equation shown here, the one thing that pops out right away to me is that hydrobromic acid is a strong acid. Nothing else really pops out at me, and that signals to me that the reaction is going to go in the reverse direction primarily, because it's going to move away from the strong substance, as the strong substance will ionize completely.
So why is that reversible?
because the strong acid's on the right side as a product, so the reaction will run away from that because that will ionize completely. If it's ionizing completely.
Not going to get completion?
No, because even when you generate some proton and some bromide ion, the proton here hooks up to the acetate ion to generate acetic acid. Is acetic acid strong or weak? It's weak, so that readily doesn't go in the forward direction. It stays together more than it separates. So as a result, the reverse reaction is favored here. That they could ask you. So if they ask you something about it, look for the strong acid and move away from it. Otherwise, they'd have to give you more data to work with, and I'll show you that later on. If you look at the relative strengths of some Bronsted-Lowry acids as well as their conjugates, you will find of the strong acids, the strongest of the strong is hydroiodic acid, and we'll talk about why that is. So you can see the acid strength here. Keep in mind hydrofluoric acid is a weak acid. What is illustrated here is something that you were asking about, JJ. If you have a strong acid, let's say HA, it will ionize completely, so the concentration of the acid is equal to the concentration of proton. And basically with a strong acid, it doesn't stay as a unit, but rather all the ions separate out and move freely, hence a good conductor. If you have a weak acid, such as HB, and the nomenclature here is not great, it doesn't ionize to any appreciable extent. So most of it stays together, the two pieces as a unit. There is some ionization, but it's minimal.
So that's reversible?
So this reaction, if you looked at it, would highly favor the reverse direction, and it is a reversible reaction. So it's actually illustrated poorly. Let me see if I can smack an arrow on there. It's actually the reverse reaction that's heavily favored. Maybe that would be better. I also don't like their HA, HB nomenclature, because usually weak acids are denoted HA, but this is what was in your book, so I grabbed it. Now, when you're looking at ways to detect acid strength, there's more than just memorizing, oh, strong acid, although that can be helpful. Strong acids will have a large Ka value. Weak acids will have a small Ka value. As we indicated already, equilibrium far to the right, equilibrium far to the left. We indicated that the concentration of proton in strong acid is almost the same, and for our purposes it will be. Here you will see that the concentration of proton is significantly less than the initial amount of acid that you started with, and you'll see that quantitatively very soon. What you'll also see is the stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. And you can compare that strength to water.
So strong acid is far to the right because it ionizes?
Completely. With your binary acids from group 17, hydrofluoric, hydrochloric, hydrobromic, hydroiodic, in terms of increasing acid strength. From group 16, now this is water, hydrosulfuric, hydroselenic, hydrotelluric, hydronitric, hydrophosphoric. So those are all binary acids comprised of H and the anion, or I guess I should say non-metal would be safer. Down a group, the strengths of binary acids increase. In order for this acid to form a conjugate base, it has to donate its proton. So you want to consider the bond energy here. How strong is that bond? You've got to break that bond. The lower the bond energy, the more likely the bond is to be broken, the stronger the acid. What determines the strength of that bond is the radius of the atom going down a group. So as you go down a group, the atomic radius gets larger because the valence electrons are farther from the nucleus with more electron shielding. As that radius gets larger, this goes back to like one very pregnant person trying to hug somebody else. That little person would have trouble getting around her midsection, and so they can't get as close together. That makes the bond weaker, and as a result, the acid is stronger. Okay, so intuitively it makes sense. Down a group, the bond energy is going to decrease. The acid becomes stronger, hence stronger acid here than here. Across a period, the acid strength also increases for a different reason. This is based on electronegativity. You know as you go across a period, electronegativity is going to increase. You know that fluorine is the most electronegative element. As the electronegativity increases, that means that the atom draws the bonding electrons more to itself. That's going to weaken the bond and strengthen the acid. So for example, across a period, hydrofluoric acid is going to be a stronger acid than water. That's because the fluorine draws the electrons in at the bond very much toward it, weakening the bond, increasing acid strength. Those are the binaries. The ternaries, ter means 3 here, like tertiary protein structure, if you remember from biology. Now what you're looking at for acid strength here is the strength of this bond. And we're going to draw some of these out because some of these kids make a ginormous mess out of. The strength of this bond is affected by the attraction of this element for electrons in that bond. So what you're going to see here is the more electronegative the element, it'll draw the electrons toward it, weakening this bond, increasing the acid strength. So for example, here, you know as you go down a group, electronegativity decreases, so acid strength decreases.
So acid's in. Wait, what?
Did I do it wrong?
No, it's supposed to increase, right?
Let's say it again.
Yeah.
We know the more as you go down a group, the electronegativity decreases. So the more electronegative element, right, draws the electrons more to itself, weakening the bond. So this acid is stronger than that one. So as you go down a group, the acid strength decreases. No, I said it right. You said it wrong.
But that's increasing.
Because this one
It's further up.
is,
acid strength.
but I said down the group. This is showing up the group. Maybe that's why you're confused.
Yeah, this switching which direction you're going.
Yeah, I said it right, but when you read it, it looked cockeyed.
It's because when
That's because I'm a dingbat. Now come on, let's, hang on. Hang on. Look, look.
I mean acid. So lower is
Yeah,
gonna
for
make
binary,
it.
yeah, but that was the opposite.
She's right.
That's, no, I said it right, but you're inferring it wrong. All right, hang on.
It wrong.
Look at these guys. Which is more electronegative? Chlorine. So that means it draws electrons in this bond toward it, which weakens this bond, making this acid stronger.
Okay.
But I said as you go down the group, it gets weaker, a weaker acid,
Yeah.
because you have less electronegativity. All right, we're good. We're good. That's why we write it down. Sometimes it makes more sense.
Why in a binary acid, when it's closer to the atom, does it decrease? Or does it
If you had, for example, let's take hydroiodic and hydrochloric acid, okay? Which has the larger radius, iodine or chlorine? Iodine has the larger radius, so these atoms cannot get as close together as these. The further apart these atoms are, the weaker the bond, the stronger the acid. It's a clipping because an acid's a proton donor, so the more readily you can donate that proton, the stronger acid you are. So the only one that's radius-based is a binary down a group. Otherwise, everything's based on electronegativity.
Why is radius more a factor here than electronegativity?
Probably because down a group, especially with the binaries, the electronegativity difference is not as great as across a period.
So, when you go down here, or
Down a group.
the
Are we doing
acid
binary or
stronger,
ternary?
ternary, acid stronger.
So if we go down a group, the acid strength decreases for a ternary. Correct.
So they're opposite.
What about binary? They increase.
Binary, it increases.
Okay.
Yeah. But see, you guys always memorize. You got to be careful with that because you have to be able to infer sometimes. Yeah, you're very big on up, down, sideways, and sometimes it just turns upside down.
Like as a ternary, you're
Yeah,
tapping
you-
into a third.
Well, actually, I think it'll make more sense in just a sec because you'll see it, the effect even greater here. And that's what's listed in 3. It says the number of oxygen atoms attached to E influences the strength of the acid. As the number of oxygen atoms increases, the acid strength increases because basically you're getting a pulling from all different directions that further weakens that OH bond. So if you look, for example, at hypochlorous all the way up to perchloric acid, you can see here that the strongest of the bunch is the perchloric because as you add more and more highly electronegative oxygen atoms, it weakens the OH bond. What I do want to show you, because this is how you can link a drawing question to an acid-base question, is when you write hypochlorous acid, you write it as such. But when you draw it, you of course draw it in this regard. And I don't think that would be an issue. I think you would be good there. However, now as you have chlorous acid, where does the O go?
The O? Or
The next O.
the O? To the O.
Probably about connected to the net.
You're going to connect it to the H?
You can.
Heck no.
Oh, it's on the other side? Oh, okay. So it's symmetrical.
And then the next O would go here, and the next O would go here. But the key point I want to make is you better have an OH bond. Otherwise, it's over, over, over.
But you never attach a note to an O.
Peroxides, yes, but otherwise the double OO is not very common. Those are 2 highly electronegative atoms, so it's not going to make for a stable structure. And that's why the Ku group is the C, double bond O, single bond OH. Okay? All right, this is the piece actually. All of what I said so far is relevant. This piece here, I don't really think you need any more. I'll mention it, but it's not something I've seen in forever. What you do see, it says if the R group connected to the Q, to the Ku contains highly electronegative elements, you see greater acid strength. So for example here, this bromine is attached right to this carbon here, whereas this chlorine's farther from the Ku group. So this acid is stronger than this. why would hydrotelluric acid be stronger than
Weaker,
hydrosulfuric?
higher radius.
So this one, they're in the same group, and it's binary, so you're going based on radius. Tellurium has the greater radius.
Weaker bond.
As a result, the atoms are farther together, the bond energy is less, so you've got it there. This piece here, I think I'm going to let go. I'm sorry it's in there at all. They're not going to ask you that. Just let it go.
Just wait, so can you spin the other one again?
Which one?
The one that was right after that one?
Before that one?
Well,
This one?
Yeah.
This one I don't think you need either. The electronegative group is very near the Cu,
Yeah.
and that's going to weaken this OH bond. No, I'm sorry. It strengthens it. It strengthens it. So it's a stronger acid.
Shouldn't the other one be stronger if it strengthens it?
No, wait a second.
If you're strength.
No, it just says the closer the electronegative group to the Cu, the stronger it is. Let's let that one go. They're not going to ask that
okay.
anymore.
Yeah, 'cause it pulls away
Yeah,
from
I'm
the
going to
OH
take
bond.
this stuff out. I haven't seen this in a long time, and I just don't think it's relevant anymore. All right, what we definitely want to talk about and review is the pH scale. So we'll go through this. This is all baby stuff from honors that I want to review with you. And somewhere in there we'll take a break. What I really want to be able to show you is the rice approach with acids and bases. That'll be new. Back to rice. It depends how much you remember from honors. So this stuff, let's get in before the break. Then we'll break. We'll do the new AP stuff. All right. In terms of the pH scale, and I don't know if all of you did this last year, so I don't want to fly through it. I want to make sure you're comfortable with it. Even pure water can conduct electricity to a small amount. You don't drop your blow dryer in the tub, right? There's actually a special ionization constant just for water. So if you look at that reaction there, you've got two water molecules generating hydronium ion and hydroxide ion, and you can write a special K just for water, which is Kw. That's going to be the hydronium ion times the hydroxide ion. These are liquids, so we don't include them. And that is a constant of 1.0 times 10 to the negative 14th, which they will give you. The reason why the pH of water is 7 is because hydronium ion and hydroxide ion are equal. So if you had x squared is equal to 1 times 10 to the negative 14, x in either case would be 1.0 times 10 to the negative 7, pH of 7, which we'll get to. You could calculate the concentration of an ion based on this Kw. It says a solution is 1.4 times 10 to the negative 4th molar hydrochloric acid. We know hydrochloric acid is a strong acid, so this concentration is equal to this one, and that's what's shown here. If you wanted to calculate hydroxide ion concentration using Kw, you could do so where hydroxide ion concentration is just the Kw over the hydronium ion concentration, and you have 1 times 10 to the negative 14 as your Kw over this, which you got from here. And the one thing I do want to show you is you can do this without a calculator. I know you're going to love it once you get used to it. For example, without a calculator, let's take a look. We can do it with fractions. Oh, yes. 1.0 times 10 to the negative 14 over 1.5 times 10 to the negative 4. It's not bad. Look. 1 over 1.5 is 2/3, correct? Times negative 14 minus negative 4 is, no, well, it's negative 10. Come on, guys, this is 7th grade math. which most of you skipped. All right. 0.67 times 10 to the negative 10. 6.7 times 10 to the negative 1 times 10 to the negative 10 is 6.7 times 10 to the negative 11. All right?
Where did 0.67 come from?
2/3.
You just know that?
I do.
Six.
Like, in your head, what did you know that 1/1.5 is 2/3?
10 over 15 is 2/3. That's how I do it. We'll do some math baby stuff in a bit.
Where did the 10 to the negative come from?
You wouldn't see that as an answer. Alrighty. Why don't you try the problem on the screen? Let's see how smart you are. I know you're smart. Come on, bonus. Let's do this one. Because this is just the tip of the iceberg. The best is yet to come.
Oh no.
I did a dance.
Oh, so first we have to do the equation. Okay.
That's what I did.
What's this?
Oh yeah, you do the equation.
Plus
Okay, so
Jay, did you want to
I'm doing it in my head.
He's doing it in his head as he roams around the classroom blocking the board.
Wait, that's an acid. Oh, wait.
Did you get it?
I'm trying to do the equation for this.
You can always check it at the end, too.
We do that on the test tomorrow too.
With your brain, yeah. You won't have time, though. Test is a little lengthy. You got a boogie, boogie, boogie.
Which
No.
part is longer, part 2 or part 1?
Part one. What? You just said boogie boogie boogie. Yeah. Cutesy question.
They're all wonderful questions.
I love all my children.
Yeah, where'd you get?
You don't have any children.
Exactly.
Exactly.
That's fake life. Wait, so those are the same. Okay. So you can take that out.
What'd you get?
3.3 times 10 negative 14.
Oh, oops. That's why. Are you doing creepy? We're in this class?
You always do that. Like, that's like such a mean grade.
Because it's an A.
That was weird. You feel better on yourself.
Yeah, me too.
Well, you know you're smart.
You're smart too, you're in this class.
Because I don't have the notes.
JD, did you print out the notes?
No, I said there's a one note.
This one note has it.
Wait, so what's
Did
the
you get what I
equation?
got?
What's the equation?
This, Kw is equal to proton times hydroxide ion.
So what did
The proton was basically given because the strong acid is the same as the proton concentration. I was lazy with my numbers here, but I got back to my siggies here. And actually, I should have M for molarity. That's sloppy.
Wait, so hydroic acid is a base?
Hydrobromic acid is an acid, right?
Yeah.
Yeah, wait, so where did you get
So hydroic acid. Where'd you get protein from? Oh, because
Well, they're gonna be equal on
Go through what?
Yeah, what's like the actual equation for?
Yeah, where are you?
Hydrobromic acid? This equation?
Oh, that's right. Yeah.
And these two concentrations are equal.
Yes. So why do you have hydroxide?
They asked for hydroxide ions. It says calculate hydroxide ion using the KW expression. That's actually not that common of a question. Yeah, no, not that common of a question. We're going to get into pH and POH calcs. Let's do a couple before the break. It was 1909 when Sorensen talked about pH. I don't know. Don't make fun. They might not like your name either. pH stands for power of the hydrogen ion. It was a man.
It's Soren the son of Soren.
Proton concentration is equal to 10 to the negative pH. Okay?
We can memorize that?
Yep.
Yep.
They do give you some stuff. Let's take a look at what they give you.
I think they give you
I think they give that to you. Yep. This is what they give you. Take a look. They give you everything. Look. Almost everything. pH is equal to negative log of proton concentration. So then you could take the inverse of the log. So proton concentration is 10 to the negative pH. POH is negative log of hydroxide ion concentration. So OH concentration is 10 to the negative POH. The sum of pH and POH, pH being a measure of acidity, is equal to 14. This is Henderson-Hasselbalch we'll get to later on. All right. Very, 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 very simple. It says calculate the pH. So you're looking for the pH. You're hoping to go after this formula of this acid with the concentration of 1.5 times 10 to the negative 4. The first thing you want to look at is hydrochloric acid a strong acid? Yes. So it's a strong acid. It ionizes completely, which means the proton or hydronium ion concentration is the same as the acid. Then it's plug and chug. pH is equal to negative log of. I do want to point something out. You're not going to be happy, but it's easy. Several things, and yes to both of you. For example, if you have a proton concentration of 1.0 times 10 to the negative 4 molar, if you have 1.0, the pH is going to be 4, essentially the absolute value of the exponent. This is 2 sig figs. Sig figs for pH and POH start after the decimal point. Okay? Now, in this problem, you have concentration of proton as 1.5 times 10 to the negative 4 molar. You don't have 1.0 here. You have a little bit more. And that means that your pH is going to be 1 less than this, so 3 point something something. You don't have to figure out the something something, although the closer to the 1, the greater these numbers are going to be. But you have to be able to go from this to at least the 3 piece.
Wait, can you say that one more time?
Yes, the whole you understood the first part, right?
Yeah, with the same.
Okay. So this number is greater than 1, but just a smidge. But even if it's 8.0 times 10 to the negative 4, the pH here will be 3 point something. The closer this number is to 1, the bigger these numbers are. The farther from 1, like 9.0, it'll still be 3 point something, but these will be smaller. That they're not going to get so technical with. 1 less than this if this number is greater than 1. And you'll see numerous examples here I'll walk you through. All right? In addition, with this problem here, pH is equal to negative log of the proton concentration. So negative log of 1.5 times 10 to the negative 4 molar. pH is going to be 3.82. 2 sig figs after the decimal point corresponds with 2 sig figs in the concentration. All I asked for here was pH. But if I asked for pOH, how would you do that? Right. Now, in regard to the sig figs are going by these decimal places here. So you would have 10.18. Okay? I just don't know how much some of you did with pH and pOH last year, so I don't want you to be left out to dry. Not much. All right. The other thing you want to be comfortable with is it says calculate the hydronium or proton ion concentration in a solution with a pH of 2.19. Hydronium ion concentration is 10 to the negative pH, so you would throw that up here. In your calculator, you'd hit 10 negative. You have it should be the inverse of the log button. So it's here. It's going to be here, negative 2.19. Yeah. It's a 10 to the X button. Oh. Well, you know what happened? That's better. Yeah. All right. So also with sig figs, you've got 2 sig figs in that pH. They start after the decimal point, so it's 6.5 times 10 to the negative 3 molar. And that's what's given. The other thing you want to be able to intuitively see is if the pH is 2 point something, the exponent is negative 3. If the pH is 5 point something, the exponent would be negative 6. So you want to see that correlation. Why don't you try these 2 problems at the top of your screen, and then we'll take a break. There are a few other things I want to show you, get your quizzes back, etc. But try those 2 problems. I'll do them on the screen so you can see. Try and guess the answer and then plug it in. Or close to the answer, I should say.
So you're really concerned about the first number in front of us?
Yeah, because that could be in a multiple choice setting.
Yeah, I know. So deep. I mean, serious. No, I mean, carry on. Carry on. Seriously, when Melissa did, everybody's like, Austin? Because of their hairy arms, arm hair.
Did you get it? Yes, yes? All right. All right, let's take a short break. And we'll pick up with the POH, and that's also honors level work too. So we'll see how far we can go. I'm going to leave the videotape rolling so I don't have to double load. I've got your quizzes here. Many of you did quite well on it. I do believe your mean was slightly higher than period 2, although they were pretty consistent. Here we go. Who wants to give them out? Thank you.
Okay.
So it says using KW. So KW is equal to that.
Does this go with this? Or are these like two separate?
There are two separate problems with the same general premise. So based on the fact it says the KW expression, you will use this expression.
Oh, water.
But I want to replace this with that?
I mean,
This concentration.
Pedro. Pedro.
I dropped that in, and this is always 1.0 times 10 to the negative 14.
What is?
You said it was a
KW
mixture
always
stream?
1.0 times 10 to the negative 14.
It was, wasn't it?
Yeah.
So you would have
No.
that
Are they
divided
just
by
not
that
mixture
to get
three?
that.
No, it wasn't that.
Oh, okay.
It's this one.
Then it doesn't work like that, and that's what we're going to get to now.
You're really good at this next test. I mean, the lab's gonna bring my grade up too.
Yeah, the labs are delicious.
I think I might be 105.
I did speak with Flynn today because you guys didn't really notice any color change with the temperature alteration, right?
Also, we didn't do anything with gas solubility.
Yeah, no, we didn't do the increased stuff. But I spoke with them today, and they said, well, just try and mix the solutions initially before you've played with them every which way. So I'll try that and see if it works better, and if it does, we'll demo it off.
Dr. K,
Yes.
can you explain to me stuff? What is this referring to?
They asked for the initial. You gave the equilibrium, but in the question it asked for the initial. So once you got the equilibrium, you knew what X was. So while you sort of did this pucker, I'm not exactly sure how to, yeah. Once you had this true, this wasn't the true here.
So then you would do the original minus
The value decreases because with the shift in the reverse direction, the products get depleted, so their amount increases. The reactants get generated, so their amount increases, resulting in a decrease in Kc. Yeah, that wasn't explained. I think they were asking about an increase in hydrogen gas. You don't want to touch that one initially because it really they are, but you gave me these as your first two, so I looked at the first two. So you wanted me to pick which ones?
I put stars next to it.
Did you want me to pick which ones were the best? You're not going to get away
Which
with
ones? What do you mean?
Oh. Okay. I see it.
Alright, let's look at this.
Yeah, I can. The left?
I gotta look at this.
You wanna go?
We're not going anywhere.
I don't think you'd be.
All right, another minute and let's pick up. Told you we should have started the other day.
I had a lot of questions.
I'll save some time at the end. I just want to do I at least want to get through the honors review stuff.
It was mostly about the lab, the pre-lab.
Can you do B? Or just tell me, actually don't look at mine. Mine's awful.
Whose phone's on my desk?
Oh, that's my phone.
What was this? Two. You get it?
This one is all in the wrong way. Okay.
No,
This
there's a question
down here.
So what happens initially is that the rate, we don't have any of the product initially, right? Because you start at 0. So initially, the rate of the forward reaction is greater than the rate of the reverse reaction. Then as you use the product, you've used up reactants, so then you're going to shift backwards, and the rate of the reverse reaction will be greater than the rate of the forward. At equilibrium, what can you say about the rates? They are, can you say all of that?
Well, I referred to the picture more, like talked about the actual little letters in the boxes. So I probably confused it. Because I knew that.
Did you get B2?
Read what you wrote.
Alright, I got it.
B2. My mistake was subtracting it back to
Yeah, you have to. Because if you think about it,
yeah.
yeah.
I think
So
you
E is
called for
equal
time.
to I plus C.
Yeah.
And so if you're solving for this, then you'll subtract, but this is a negative, right? Well, it's a 2-to-1 ratio, so the increase has to be
I mean, I had this one, but then I didn't put it
That's why I didn't do it. That's why I didn't put that one. Wait, if you're adding X, then it wouldn't be losing it. You would have least.
That's why I put that.
Yeah, so yeah, so I would-
You didn't even
Oh,
check
yeah,
the
maybe
hyper.
not fully established before it also do that on I actually didn't even realize that. I'm not sure I realized it. I see what you're saying, but yeah, the increase is really
We just reasoned our own logic.
Yeah, and we wouldn't know that this was negative three.
Good question.
So whatever reason.
Alright, we'll take questions at the end. Just circle where you are. Jennifer, Don.
And you think, well, the other minus 4x, but we were thinking, well, that's
Quick question. So the forward reaction uses up the reactants. So then it just starts going the other direction.
Right, because then you use up the reactants, and then your products that react with each other, so then they regenerate reactants in a reverse. Alright, let's pick back up, and we will reserve some time at the end for questions.
No. I have to go.
And again, this is going to be a lot of review from honors, just in regard to the pH scale. Some additional formulas that we've talked about. Again, POH, a measure of basicity, is equal to negative log of hydroxide ion concentration. If you want the hydroxide ion concentration, it's just the inverse of, or 10 to the negative POH. The sum of POH and pH is equal to 14, and that's equal to the pKw. The pKw you can get from the negative log of Kw. Kw we established at 1.0 times 10 to the negative 14, so pKw is 14. And we'll get into pKa, pKb a little bit more in the weeks to come.
So what's the PK?
pKw is 14. It's negative log of the Kw. Kw we established at 1.0 times 10 to the negative 14.
Is KW given or no?
Yes.
Oh, so positive log would be negative.
Yes. Is he bothering you?
I promise I'm not good for it. At least my mom says I am.
The pH scale goes from 0 to 14, And if we look at a pH scale, the acidic range, neutral at 7, the basic range greater than 7. A lot of products that you use in the household, we'll go through here. The smaller the pH, that is the farther away from 7, the more acidic. So a pH of 1 is more acidic than a pH of 14. Your stomach acid has a pH of about 2. You never want to see a kid sucking on lemons. Lemons is very acidic, pH between 2 and 3. Kids do that. They suck on lemons. So bad for your teeth. Bad for your teeth. Vinegar has a pH. It's fine like in water or tea, but you don't want to just drink a lemon. That's gross.
Wait, why is that bad for you if it's close to stomach acid?
But it's very acidic right on your teeth. It's right on your teeth. Yeah.
Drink with your teeth. Drink with your throat.
Just like
down a straw.
Milk is getting much closer to neutrality. It's still on your teeth.
that'd be hard to like.
That's why with people with eating disorders like bulimia, they can spot it right away because the back of their enamel is gone from all the vomiting. Yes, because they're basically vomiting stomach acid, so the acid from the stomach eats away at your teeth. That's the first thing they'll look for. A dentist will catch that like this.
No way.
Yes way.
Fast.
Blood also, you also have to monitor blood pH. You don't want it to fluctuate too much. It can result in acidosis. So blood pH is typically between about 7.2 and 7.4. Your cleansers tend to be more basic. They're slippery, so they take grease and other things off. And then lye or Drano, 1 molar sodium hydroxide, has a relatively high pH. Again, the greater the pH, the more basic. The lower the pH, the more acidic. Here's a very simple problem worked out with one little trick to it. And again, this would be at the honors level. It says a student determines that calcium hydroxide in its saturated aqueous solution has a pH of 10.52. Calculate the molarity of calcium hydroxide in its saturated aqueous solution. First of all, they give you the pH, but calcium hydroxide is an acid or a base? Base. It's got hydroxide in it and it's strong. It's a strong base, meaning it ionizes completely, but you have to be careful here. So we're going to go after the POH here because it's a base. You can get the hydroxide ion concentration by doing 10 to the negative POH. So that's the concentration of hydroxide ion. However, what do you know about the mole ratio between calcium hydroxide and hydroxide ion? It's 1 to 2, so be careful there. They ask for the molarity of the base, and you need to do the stoichiometry here in order to get the concentration of the calcium hydroxide.
So you need an equation.
Exactly. This one is much, much easier. Try and do that problem. Go. Go, go, go. Look at what they give you. Look at what you want to know. Watch your siggies. You want that? But I want you to do this problem. Obviously not the one that's been done. Hey, goofballs, do it. Yeah, this one's easy. Did you watch your Siggy Wiggies? Yeah, this one's too easy. Are you done? That one's much easier than what I gave you. Oh.
You show the word?
Sure.
This one's safe.
Wasn't much to
Yeah,
it.
that's what I thought. Okay.
Didn't even need a calculator.
Wouldn't it be 1.0?
No. 2 sig figs, 2 sig figs. Sig figs for pH after the decimal point. Oh. They're very generous on pH sig figs, though. You can be plus or minus 2 off.
It's okay. Yeah, I don't think we get any worse than that.
Nope. All right. This problem, basically all of this is the same thing, just combining different things you learned from honors. I'll walk you through this example and we'll give the next one a shot. It says, what is the pH of a solution containing 2.65 grams of barium hydroxide in 735 mils of aqueous solution? Assume that barium hydroxide dissociates completely. So we want to know the pH. That's what we're looking for. We're given the mass and volume of a base. So if you're given a base, you're going to have to go after the hydroxide ion concentration initially. And just to make this problem a little trickier, you've got a group 2 hydroxide, so you've got that 1 to 2 mole ratio of base to hydroxide ion. So the first thing you're going to do is get the molarity of the base. You'll convert the mass to moles, you'll divide by the volume, and now you've got the concentration of the base. In order to get the pH, you have to get the pOH. To get the pOH, you need concentration of hydroxide ion, and this one wasn't 1 to 1, but rather 1 to 2. So you multiply the molarity by 2. Now you have the concentration of the hydroxide ion. Once you have that, you can do negative log of it to get the pOH. Note the 3 sig figs after the decimal. 14 minus that'll give you the pH. Let's walk through this one. This actually is almost identical to it. I'll leave that one up and try the one in green.
The one before, why did you do 1.0 times that? Why wasn't it just 10 to the negative 3?
Same thing,
Yeah, it's the same thing, but why did you do it?
because that's the way my brain worked.
Oh.
Same
Do
thing.
you don't have to have it?
Nope.
Okay. Well, I was curious. I didn't...
Are you done? JJ, are you done?
I'm doing it in my head now.
Really? You can do this one in your head?
Well, if I know the steps and I know how to do it, then yeah.
Okay. After he coughs on it.
Here, I feel the smell.
No smell.
I don't think
Strontium, 87 point, no. 86.72?
JJ, you didn't know that it's
No, 87.62.
how do you figure out the moles?
I don't. I just know I have to find it. It's easy. Like, you just look at your periodic table.
Well, it's 34 plus 100. It's 34 plus 100.
Yields SR2 plus 2
And you get the iron molarities. You get your moles and divide. Well, you get your molarities and divide that by 2 in your ratio.
121.
You gotta find molarity first.
I have a different calculator.
Oh, the big one, yeah. Molarity twice as much.
Times 1 over
No, divide by.
No, you
No,
multiply.
multiply by 2, yeah. Oh, I have to do it in my head, yeah. Multiply by 2. And then you do negative 4 or whatever it is.
Negative log of whatever you found.
And boom.
No, wait.
Negative 6 things.
That gives.
Just do it.
Do it, Austin.
But then you gotta subtract
Oh,
the
yeah,
14.
because that's the thing.
Okay, we're smart in concept.
So late.
What'd you get?
Wait.
What do you want to know?
What's the mass of strontium
Strontium or strontium hydroxide?
hydroxide?
I got 121.636.
Oh, yeah. 121.636.
These calculators are not easy.
Did you get it?
Yes.
Ooh, it's
Yes.
got cut off a smidgies. How's that?
10.006.
Huh? Did you get what I got?
Chris, I don't like your calculator.
Oh.
You should try. Oh, yeah. Okay.
Did you need a calculator,
No.
JJ? Alright.
Oh, because I did it.
What did you get?
On the screen.
0.064.
Did you get what I got?
I did. Yeah. You got that? Here.
Yeah.
Finally? No, let me see it. I want to see it.
So like, remember when you have to plug in like F prime of negative 2? You have to,
Are you good there? Everybody's good?
Yeah. F prime and negative. I guess. I don't remember.
okay.
I have to see the problem.
Instead of making it equal to negative 2, I said I made it equal to 2. That's why I missed the question.
One question.
I missed it.
Oh, two questions.
All right, the last thing I want to show you today
Okay.
is the tip of the iceberg.
Answer, and then I reset for different answers, and then I got it. Never mind.
The last thing I want to show you today is the tip of the iceberg for understanding acids and bases at the AP level. I'll show you one or two problems and then we'll pick up here, and this will be predominantly what the quiz focuses on, although writing the equation, writing a Ka or Kb expression will be assessed as well, but it'll pick up here. So we want to look at equilibrium solutions of weak acids and weak bases. And in this case, weak acids and weak bases don't ionize completely, so you cannot say that the concentration of acid is equal to the concentration of proton. That's where things really are going to change here. You're going to have to calculate the proton concentration and then the pH, or the hydroxide ion concentration, then the pOH. So this is going to be a little more involved. As I indicated previously, those Ka or Kb values are in your textbook, either on 644 or 663. There also are some tables in the appendices at the back of the book, so that's where you'll find everything there. Alternatively, you can go online and print out a table if it's easier for you. If you want me to find one, I can pump it to Edline. pKa is going to be negative log of Ka. Very large values of Ka will have small pKa values. Same thing for Kb and pKb. We'll come back to pKa and pKb when we get to Henderson-Hasselbalch. When you're working these types of problems, there are a few things you want to consider. You want to look at the major species that are in solution. We said if you have a strong acid, it ionizes completely and all you've got is proton and anion. We want to look at the dominant reaction. Is it the forward reaction that's favored? Is it the reverse reaction that's favored? You want to know whether the reaction's at equilibrium or it's going to completion. That is it weak or is it strong? You want to react all major species until you're left with an equilibrium reaction. We'll take a look at that, and then we're going to solve for pH. The steps involved are indicated here. Rather than read through these and confuse you, we're going to walk through these and we can refer back to them as we go. The first example is done for you. It's going to look very overwhelming, and then we'll walk through one and you'll see it's really pretty easy. Our approach is rice, exactly what we looked at in the previous chapter with reaction, initial, change, equilibrium. One thing we want to check right away, and it's always going to work, is the 5% rule. It says if the ratio of molarity of acid over the Ka, which will be given, is greater than 100, you can ignore the x that's added to or subtracted from the number, because x is going to be so small, it's going to be less than 5% the molarity of the acid, that you can do the problem without it and get the same answer. You do need to indicate that x is less than 5% the molarity of the acid, and I'll show you what I mean here. You can calculate the pH from a concentration initially and from a Ka or Kb. It says determine the pH of 0.250 molar propanoic acid. The Ka is given. That's all they're going to give you. First thing you're going to do is set up your rice table. You're going to show the ionization just like we did at the very beginning of class. The initial amount is provided at 0.25 molar, and you don't have any product at the beginning. The rate of the forward reaction is going to occur to utilize the reactants. We're going to take away 1x here. Why do we take away 1x here? Because we're going forward and the coefficient's 1. And for these acid-base problems, the coefficients will be 1.
How do you know that it's only the forward direction?
Because you don't have any product to start. You're going to add an x here and an x here, and these two are the same. E is equal to I plus C, so you've got this, this, and this. Here's your Ka expression. We wrote those at the beginning of class. One thing you want to check is if the molarity of the acid, which is given, over the Ka, which is given, is greater than 100, then x is less than 5% the molarity of the acid, and we can cancel that negative x that's subtracted from a quantity. That's going to make the solving process so much easier, and you will have to do some of these without a calculator. I'll give you some simple examples. Now you have x squared, because each of these is x, over the initial amount. We got rid of the minus x because x is less than 5% the molarity of the acid. If you had a base, it'd be molarity of the base over the Kb. And this was the Ka given. You have this times this is equal to x squared. You take the square root of both sides, and you have x is equal to this. Now x is equal to hydronium ion concentration. So negative log of this gives you the pH. And I'll walk through one from scratch so you can see it step by step. But it is as easy as that. It looks awful. It's really very simple. Let's take a look at this one from start to finish, and then we'll call it a day, and I'll answer any questions that you may have, probably more about the quiz than this. It says, what is the pH? So we want to know the pH. The concentration of hypochlorous acid is 0.0100 molar. And the Ka is 1.1 times 10 to the negative 8. Now when you have such small Kas, you're going to ignore the x. It's a done deal, but we'll prove it. To start this problem off, I'm going to make a rice table, and I'm going to show. You can do it with or without water. Actually, I'll put the water in because for the bases you need it, and so I don't want to confuse you. Doesn't matter what you put first. The initial concentration here. And now what are you going to do? You got zeros here. You're going to subtract, add. Now you need to see if you can get rid of that x. So we said the molarity of the acid over Ka has to be greater than 100. We have 0.0100 molar over this, and that's much greater than 100. So X is less than 5% the molarity of the acid, and as a result, I can get rid of this. My Ka expression is going to be the products over the reactants. We're going to have 1.1 times 10 to the negative 8 is equal to x squared over 0.01, and this is a perfect one to do without a calculator. We've got x squared is equal to, this is 1.00 times 10 to the negative 2. So this times this is 1.1 times 10 to the negative 10. And that's very close to 1.0 times 10 to the negative 5. And it is actually. And what is that equal to? What is X equal to of importance? Concentration of the hydronium ion, because we know that pH is equal to negative log of the hydronium ion concentration. So your pH is equal to 5.00. So it looks awful. One thing you're also seeing is that the concentration of hydronium ion, this should have a capital M for molarity. The concentration of hydronium ion is much smaller than the concentration of the acid, which is expected based on the fact that equilibrium lies to the left. All right? It's a weak acid. We still have about 6-7 minutes. The clock in the back is fast. We'll pick up doing one of these to come back after the test next week, and then we'll get into this a little bit more. And basically, what we talked about today in the very beginning of next time's piece is what you'll see on the quiz, but I'll tell you exactly what's on the quiz on Monday next week so you're comfortable with it. You should have a basic idea now about acids and bases, their similarities and differences, strong versus weak, and we'll put it all into perspective next time.